Okay, so let's talk about the most incredible highway system you can imagine. And it's not made of asphalt, it's inside of you. It's not just simple plumbing, it's a living, dynamic network that is constantly, and I mean constantly, working to keep you alive. Today, we're going to take a journey down that highway. And just to give you a sense of the sheer scale we're dealing with, get this. If you could take all of your blood vessels, every single one, and lay them out in a straight line, they would stretch for 100,000 kilometers. That's enough to circle the entire planet 2.5 times. It's this absolutely massive, closed-loop highway system all packed inside your body. So you've got to wonder, right? How in the world does your body manage all of that? How does it build it, maintain it, and direct all the traffic along this enormous network? Well, to find out, we're going to follow a single drop of blood on its absolutely incredible round trip. Our little adventure has 3 main parts. First, we'll blast off through the high-pressure arteries leaving the heart. Then we'll arrive at the destination, the tiny capillaries. And finally, we'll take the long, slow road home through the veins. But before we hit the road, let's look at how the highway itself is built. You know, most arteries and veins share this basic 3-layer design. On the inside, you've got the tunica intima, which is this super slick surface so blood can just glide along with almost no friction. The middle layer, the tunica media, is the muscle. It's the workhorse that can actually change the vessel's diameter. And then on the outside, you have the tunica externa, which is like this tough, protective overcoat that anchors the whole thing in place. Now, the thickness of these layers changes a lot depending on what job that particular vessel has to do. And we're off. With one massive beat of the heart, our blood drop is shot into the aorta, the body's main superhighway. Welcome to the fast lane, the high-pressure world of the arteries. So arteries have one primary mission: carry blood away from the heart. And because they're the first stop right after that powerful pump, they have to be built to withstand some incredible forces. Their entire structure is designed to handle this constant pulsing pressure. You should think of the biggest arteries less like rigid pipes and more like elastic balloons. Seriously, with every beat, they actually expand to absorb that huge surge of pressure from the heart. Then, as the heart relaxes, their stretchy walls snap back, which pushes the blood forward and really smooths out the flow. It's a brilliant design that softens the blow, protecting all the smaller, more delicate vessels downstream. Now, not all arteries are created equal. They specialize as they get further from the heart. Right at the start, you have the massive elastic arteries. Their job is to just soak up that initial pressure blast. They then branch into muscular arteries, which have these really thick middle layers so they can actively control where the blood goes by squeezing down or opening up. And finally, we get to the tiny arterioles. These guys are the ultimate gatekeepers. They are the ones that really regulate the blood pressure for the entire body. Okay, so after squeezing through those tiny arterioles, our blood drop has finally arrived. It's at its destination, the microscopic side streets of the body, the capillaries. And this is where the real work gets done. I mean it. This is the whole point of the trip. In these vessels, which are so thin, it's hard to even imagine, our blood drop can finally do its job. It drops off a package of oxygen and nutrients to the cells, and in return, it picks up the cellular trash, like carbon dioxide and other waste. It's the ultimate delivery and pickup service. And here is a fantastic example of form-following function. All capillaries are designed to be a little leaky, but how leaky they are depends entirely on where they are. Continuous capillaries are your standard model, found almost everywhere. Then you have fenestrated ones, which have little pores, kind of like a strainer, perfect for the filtering that happens in your kidneys. And then there are the sinusoid capillaries. These have huge gaps, big enough for entire blood cells to squeeze through, which is absolutely essential in places like the bone marrow, where new blood cells are born. Okay, here's a cool little paradox for you. If you look at just one vessel, a single capillary is by far the narrowest tube in the whole system. So why is the blood flow the slowest here? Well, the secret is in their sheer numbers. The total area of all your capillaries combined is absolutely massive, way bigger than the aorta. Imagine a 10-lane superhighway suddenly splitting into 1 million tiny country roads. All that extra space slows the traffic to a crawl, and that's exactly what you want. It maximizes the time for that all-important nutrient exchange. All right, so the delivery is complete. Our blood drop did its job. But in the process, pretty much all of that initial pressure from the heart has fizzled out. It's now stuck in a low-pressure, slow-moving traffic jam. And it has to get all the way back to the heart, often fighting gravity the entire way. How on earth is that even possible? And that brings us to the final leg of our journey, the venous system. The return trip faces a totally different challenge. It's not about surviving high pressure anymore. It's about creating movement where there's almost none to begin with. When you look at them side by side, veins are basically the polar opposite of arteries. They don't need thick muscular walls because the pressure is so low. In fact, their walls are pretty thin, and their inner passageways, the lumen, are much wider. But most importantly, especially in our arms and legs, veins have a secret weapon that arteries don't have, these amazing little one-way valves. Now, because veins are so wide and the blood moves through them so slowly, they actually end up holding most of your blood at any given time. Their thin, stretchy walls can easily expand to hold all that volume, which makes them the body's primary blood reservoirs. No, really, think about that. As you're sitting there right now, about 2/3 of all the blood in your body is just kind of hanging out in your venous system. And this reservoir is super important. If you suddenly need to, say, run away from a threat, your body can squeeze those veins, pushing all that stored blood back toward the heart and into active circulation. So, how does this low-pressure blood actually make it home? Well, the body uses a few ingenious tricks. First, you've got those one-way valves. They act like gates in a canal, letting blood go up, but snapping shut so it can't fall back down. Second is the skeletal muscle pump. Every time you walk or even just tense your leg muscles, you're squeezing the deep veins and literally milking the blood upward, past the next valve. And third, there's the respiratory pump. The simple act of breathing creates pressure changes in your chest that help pull blood up from your abdomen. It's a brilliant multi-part system. So our blood drop made it all the way back home. The whole journey was made possible by a few fundamental rules of the road, the basic physics that govern this entire highway system. It really all boils down to a constant battle. The goal, the thing we're trying to achieve, is blood flow. We need to get a certain volume of blood to our tissues every single minute. That's the objective. The engine that drives this whole thing is blood pressure. That's the push, the force that the heart generates to get the blood moving in the first place. But there's always something pushing back, and that's peripheral resistance. You can think of it as friction or drag. For blood to move at all, pressure always has to be stronger than resistance. So what causes this resistance? Well, a few things. How thick or viscous your blood is, for one. How long the vessels are is another. But the single most important factor, the real game changer, is vessel radius. And this is where it gets crazy. The relationship isn't linear. If you cut a vessel's radius in half, you don't double the resistance. You increase it 16 times. That is an unbelievable amount of control, and it's why those tiny muscular arterioles are the true traffic controllers for the entire body. So we end right where we began, with this mind-boggling 100,000-kilometer highway. After our journey, we can see the answer to our question. On this vast, complex network, the body doesn't direct traffic by building new roads. It does it by constantly changing the width of the roads it already has. That dynamic, moment-to-moment control of vessel radius, that is the real secret to managing the body's absolutely amazing highway.